Okay, so we're going to deal with the instantaneous rate of change right now. So here's the big key. Couple things. First of all, rate of change. What do you think about when you hear those words? Of course, it's a fraction changes of two different changes. So what's the difference between, so that's a rate of change. Now, we know that rate of change is one other value we have in math, and that's slope, where we could take in function form the change in the y values, the function values, divided by the change in the x, the domain values. Now we're going to alter that just a little bit later. So let's take a look at what we mean by that. So coming over to here, so here's for number one of the functions. So here's what we got. Here's we got the line, here's a, and here's f of a. Instead of a and b, let's use h as some change in, some horizontal change. And so this is a plus h, and then that is the function value at a plus that h value. Okay? So right now that's listed as 1. So we can find the slope for there. Now you can tell that's a rate of change, but it's not at an instant. It's a here to here. It's an average rate of change. So what happens? So to get to that instance, we're going to go ahead and take that rate of change, that h value, and make it smaller. Okay, you could still see it's still a slope, still a change in y, change in x. So you still get that same rise over 1, delta y over delta x. And you keep getting closer and closer and closer and closer and closer. It's still two different points, still an average, but two real close values right there. But as h approaches 0, now we're at 1 point. How do we find the slope of 1 point? Well, we don't. We can't. Even if there's 1 point right on top of each other, can't do it. They're really close. That's still a small change. But again, what we want to do is we want to take that h value, this horizontal distance, that change in x, and make that approach 0. Approaching 0 is the key. So let's go to here. Here's for 14. But before we do that, so that function value we were talking about, that slope, was f of, we'll use a plus h, and then minus f of a. So instead of b, we're going to use that a plus h. And then we had a plus h minus a. So that was the slope at the two starting points. Now let's clean that denominator up, because plus a plus h minus a, the a's are going to go away. Bye-bye. And then again, what did we do with this? Well, remember we took that and made h approach 0, so that delta x approaches 0. And how do we do that? By making the limit. So this limit here looks weird. This is our limit for our instantaneous rate of change. So what do we do with these? Same thing. There's nothing different. So we're just going to take the limit in 14 as h approaches 0 of f of x plus h. Actually, if we do it the way we have here, let's, instead of using x, 1 plus h minus f of 1 over h. Now that doesn't look much difference. Well, what do we do with that? Okay, so again, let's remember, what do we do in function notation with this stuff? With this stuff, now that goes in to every x. So for that first f of 1 plus h, the limit as h approaches 0 of 2 times, instead of x, we're going to put 1 plus h squared, minus 2, instead of x, 1 plus h, plus 2. So that there, this here, is this right here, minus, plug in 1 into the x's. 2 times 1 squared minus 2 times 1 for x plus 2. So this here is this right here over h. Now, if we go ahead and right now think, oh, let's use direct substitution. I can tell you for a fact, this format, this notation, will always give you that 0 over 0. No ifs, ands, or buts about it. It has to. It will. You don't even bother trying. Just go ahead and. So, what we know we have to do something with it. Well, let's do the simplifying. So, do a couple of things at once. I'm going to square this. So I got 1 plus h quantity squared. That's 1 squared plus 2 times 1 times h, or 2h, plus h squared. Then I'm going to distribute the 2. So 2 plus 4h plus 2h squared. Distribute the negative 2. Negative 2 times 1, negative 2 times h, plus 2. And this here, let's see, 2 minus 2 plus 2. Combine like terms. So limit, still haven't dealt with the limit at all. We're just changing the way the stuff looks. So 2 minus 2 plus 2 minus 2. 0 for h. Oops, I forgot we got a 4h minus 2h. And then a plus 2h squared. All over h. Common factor of h in each of the 3 terms. So it's a common factor we could reduce. We can go that factor of h, and 1 there, so there's 1 left. So that gives us 2 plus 2h. Notice no fraction. Well, we could envision over 1 if we really wanted to. Now plug in 0 for h. 2. Ta-da! Done. I know it looks like it's strange. I went through the algebra quick, but the setup is the key. In the algebra, you know, it just looks different with this limit on top of it. But it's still the same stuff, okay? So that's what we do in instantaneous rate of change. We use this limit. You're gonna see this limit a lot. Okay? So let's go ahead and do number 17 at x equals 0. So we're still going to use that limit as h goes to 0 of f of x a plus h minus f of a over h. Now that's again when we know what that a value is. Maybe some other ones will show later on what happens if we don't know what that a value is, or what happens if we're finding many multiples. We'll do that later. So plug in 0 plus h, what is, so we have f of 0. We'll actually, yeah, let's put in 0 plus h there, because then we want the practice for this. Minus f of 0. Actually, no, because f of 0 plus h ends up being f of h, which is okay. We don't mind doing that. For some reason, I had a scarecrow moment thinking that was f of 0. So, plug in h for x. Still a limit. As h goes to 0 of 1 over h plus 1. Plug in 0. Again, function notation, this stuff goes into x. Each and every x. This stuff goes into each and every x. So that's what we have here. So limit as h goes to 0. That turns out to be this here. Again, I'm telling you, this is going to be a 0 over 0. So, let's get rid of the complex fraction. Let's do it that way. The only denominator, in fact, is h plus 1, so let's multiply top and bottom by it. So h plus 1 in here. Don't forget the limit as h goes to infinity. Sorry, h goes to 0. So plug it in here, we get 1 minus 1 times h plus 1. Don't distribute the denominator. Again, the whole idea behind the denominator is hopefully we can factor. Cancel out. One minus h, oh wait, 1 minus 1 minus h over h times h plus 1. Oh, another times. Bye-bye. Now this is where we could leave a step out if we wanted to. We see the 1 here, we do the reducing, that's 1. Now if we wanted to plug right in, we can, or I'm just going to go ahead and write that one out. Oops. Plug 0 in for h. Negative 1 over 0 plus 1. So the instantaneous rate of change. So y is changing at x equals 0 at a rate of negative 1. That's what that's saying. So when we come back here, in this one, this function is changing at x equal 1, changing at a rate of 2. So y changes that instant 2. Okay? So we'll take a look at the tangent line and the other one. Okay.